Hello and welcome to Tribe Topper. In this video session, you are going to learn about specific latent heat. So, when we provide heat energy to some substance, but the temperature doesn't change, it's just the state which changes, like you're melting ice or you're boiling water, then whatever is the heat energy required to bring about that change in 1 kg of a substance, we call that as specific latent heat. So the definition would be it is the heat energy which is required to change the state of 1 kg of a substance, and the heat energy that is required to change the state of 1 kg of a substance, if you want to take it from solid to liquid, in that case it is called specific latent heat of fusion. And if you are changing the state of 1 kg of a substance from liquid to gas, then it is known as the specific latent heat of vaporization, because the change in state can be from solid to liquid or liquid to gas or even turning them back. So melting will refer to latent heat of fusion and boiling would refer to latent heat of vaporization. A very important thing you need to remember here, that when you are providing heat and the temperature rises, the state remains the same. The state does not change. But when you are heating something and the state changes, then the temperature remains the same. So while the state changes, the temperature does not rise, because all the heat energy is used up in breaking the bonds and changing the state. Now, this graph or this heating curve represents this change of state, so and the rise in temperature. So if you look at this, I'll mark this as point A. In going from A to B, the substance is just being heated up and it is in the solid state, so it remains as solid. The temperature rose from 0 or say T1 to T2, but the state did not change. Now you see there is a horizontal line. So from B to C, it starts melting when it has reached its melting point. So that means this temperature T2 is the melting point, because substance will melt only at its melting point. So when it has reached B, the temperature is the melting point. Now whatever heat you give will not change the temperature. All the heat will go in melting it. Now, once all the substance has melted and you're still giving it heat, then from C to D, the temperature again starts rising. It's an inclined line again, and it's all liquid. So the state remains the same from C to D. So I will just write down A to B, you have delta T, and the state remains the same, that is solid. B to C, you have melting. So the state changes, T remains constant. Then from C to D, again there is a delta T. The temperature rises and the state remains as a liquid. And then when you go from D to C, as you can see again, there is a horizontal line. That means temperature is not rising, it's boiling. But the temperature that you have reached at D3, D point is T3, which will be the boiling point, because the thing will boil only at its boiling point. So C to D, we were rising the temperature so that we reach the boiling point. Now D to, you can say, E. What is happening? D to E, it's again just the boiling happening, and again the temperature remains constant at the boiling point. And last is, if you're still heating it, the temperature of steam will also rise. So this curve represents that how you are going to graph the temperature versus time when the temperature is rising or when the state is changing. But please keep in mind, when the temperature rises, the state remains the same, and when the state changes, the temperature remains the same. Now let's look at a problem based on latent heat. So here we have a heater is used to boil a liquid in a pan for a measured time. The following data are available. You have the power rating of the heater, because heater is going to give you the heat energy, that is 25 watt is the power, and the time for which the liquid is boiled is 6.2 into 10 to the power 2 seconds. So first of all, I've written the power of the heater and the time for which it is used. Now let's talk about the liquid. The mass of the liquid that boils away is 4.1 times 10 to the power negative 2 kg. Okay, but to find this out, they want us to find the latent heat of vaporization. So here we first need to understand what is the formula for the specific latent heat. Okay, because whatever heat you're giving is used up in boiling, and it just depends on the mass of the liquid. So Q is directly proportional to the mass. And when you remove the proportionality sign, we get Q is equal to M into L. L vaporization, where L is the constant of proportionality. I'll put vaporization later. First, let's consider it to be just L. So what is L? L is your specific latent heat of vaporization. And how would we define it from here? We would say L is equal to Q over M. So if the mass is just 1 kilogram, then what is L equal to? That's just Q. So this gives me the definition for latent heat of vaporization. The latent heat of vaporization would be defined as specific latent heat of a substance is therefore the energy transferred to 1 kg of a substance to change its state at a constant temperature. So L is the latent heat of vaporization, is the latent heat, and it is just the amount of heat energy that is required to change the state of 1 kg of a substance. So we have the formula Q is equal to ml. So now let's use this formula to solve the problem. So as we just read, as per the given information, we have the power and time from the heater and the mass of the liquid that boils away, and we have to find the specific latent heat of vaporization of the liquid. So first of all, we will find out what is the heat energy supplied by the heater, right? Q is the heat energy supplied by the heater in this case, and that is going to be power into time, because you have learnt that energy, power is energy over time, then energy will be power into time. So 25 times 6.2 times 10 to the power 2, and solving this we get 15.5 into 10 to the power 3 joules. So this is the heat energy that has been supplied by the heater. All this heat energy is used to boil the liquid. So let's equate that, right? Boil the liquid. So we have, using the formula, Q is equal to ml. Therefore, what is L of vaporization? That will be Q over M. We already have Q with us, which is 15.5 times 10 to the power 3 upon the mass. That will be 4.1 into 10 to the power negative 2. And solving this, we are going to get 3.7 into 10 to the power 5 joules per kg. Here we don't have per Kelvin. Like in specific heat capacity, if you remember, we had joules per kg per Kelvin or joules per kg per degree Celsius. But now we have just joules per kg because there is no T involved in this. So that's all for this video session. In the next video session, you are going to learn about the gas modeling.